Welcome to this explainer. Today, we are diving straight into the buzzwords of AI to uncover how these systems actually process information. We hear terms like algorithm and artificial intelligence thrown around constantly, right? Well, today, we are stripping away all that jargon to look at the absolute foundation of modern AI. By the end of this, you'll know exactly how the technology shaping our future works, right from the ground up.
So let's kick things off by shifting our focus just a bit. Instead of asking what artificial intelligence is, let's ask a much more foundational question. How does a machine actually learn anything at all? You know, it's pretty easy to picture a computer just memorizing a massive hard drive full of facts. But true learning, that is something entirely different. It's about understanding patterns well enough to handle completely new, unexpected situations.
Let's think of the computer as a student. Machine learning is basically the process of teaching that student using data rather than handing them a rigid, step-by-step instruction manual for every single little task. See, in the past, if you wanted a computer to do something, programmers literally had to write millions of lines of strict, if this happens, then do that rules. You had to account for absolutely everything. Machine learning completely flips that script. It removes the need for explicit programming, letting the computer improve its own performance simply by being exposed to more and more information. Today, we are going to explore the three distinct teaching methods we use to train these digital students: supervised learning, unsupervised learning, and reinforcement learning.
Section 1. Supervised learning, also known as the answer key.
This first path is actually remarkably similar to how we learn as kids. It's kind of like a teacher handing a student a massive stack of flashcards with the questions on the front and the exact answers written clearly on the back. In this method, we feed the model what we call labeled data. So imagine you want to teach a computer to recognize animals. You don't describe a cat's pointy ears or a dog's snout using code. Nope. Instead, you just provide thousands upon thousands of images, specifically tagged as either cat or dog. The model studies these endless examples and learns that deep relationship between the visual inputs and the correct outputs. And once training is done, it can look at a totally new, never-before-seen picture and confidently tell you what it is. Pretty cool, right?
Now, supervised learning generally breaks down into two main goals: classification and regression. With classification, the machine's job is to group things into definitive categories, like, is this incoming email spam or not spam? Is a transaction fraudulent or legitimate? It's categorizing the world into clear buckets. Then we have regression, where the machine predicts exact numerical values based on historical trends. This is the heavy lifting you'd use to forecast next month's sales revenue, estimate house prices, or predict exactly what tomorrow's peak temperature will be. Because it's so highly accurate when given quality labeled data, this answer key method powers so many of the everyday tools we rely on. Literally, every time you don't have to manually delete a spam email, or when your bank flags a suspicious purchase across the country in seconds, you have supervised learning to thank. It even helps doctors catch early signs of disease in medical imaging. It's an absolutely massive, indispensable part of modern industry. But, and here's the catch, labeling all of that data with the correct answers, that is incredibly expensive and time-consuming for humans to do. Which brings us to Section 2, unsupervised learning, hidden patterns. So what happens when we just don't have an answer key to give our student? What if we're sitting on a mountain of raw information and have zero way to organize it beforehand? Well, in unsupervised learning, we hand the computer a messy room full of unlabeled data and essentially say, hey, I don't know what these are, but find the hidden structures and group them together. The model receives this data without any predefined answers or guidance whatsoever. It's entirely up to the algorithm to discover the underlying patterns, structures, and relationships completely on its own. Because it isn't told what to look for, the model uses some really clever techniques. Take clustering, which naturally groups similar data points together, or association rule learning. For example, a model might analyze hundreds of thousands of supermarket purchase records and independently discover that, hey, customers who buy bread very frequently buy butter as well. No human programmer told the machine to look for that connection. It just found it hidden in the noise of the data. And because it found this hidden rule, that supermarket can optimize its floor layout to drive more sales. Unsupervised learning also uses dimensionality reduction to intelligently compress massive datasets so human analysts can actually visualize and make sense of them. The crucial takeaway here is that unsupervised learning is the quiet engine behind discovering hidden insights. When a business segments its customers into highly targeted marketing groups without knowing what those groups were beforehand, or, oh, here's a good one, when a streaming service magically knows exactly what movie you want to watch next based on your super obscure viewing habits, yep, that is unsupervised learning at work. It is absolutely fantastic for exploratory analysis, showing us the blind spots we didn't even realize we had. Moving on to Section 3, Reinforcement Learning, Trial and Error. Our third and final teaching method completely drops the static data sets, both labeled and unlabeled, and instead drops the student directly into a reactive, dynamic environment. Imagine teaching a digital robot to walk. Initially, the agent, which is our learner, just makes random movements. It has absolutely no idea what it's doing, but it learns purely through trial and error. When it moves a leg forward and stays upright, it receives a reward, basically like scoring points in a video game. When it falls down, it gets a penalty. Over time, the agent improves its internal policy to maximize those rewards. This kind of experience-based learning is incredibly effective for complex decision-making in constantly changing environments. Actually, this is exactly how systems like Google DeepMind's AlphaGo defeated world champions at the incredibly complex board game Go. The programmers didn't teach the AI how to win. Instead, it simply played millions upon millions of games against itself until it became a master. It's also the foundational logic behind how self-driving cars and autonomous systems continuously learn to navigate unpredictable, busy city streets. They learn by interacting directly with their environment. However, we definitely need to talk about the limitations here. Letting a computer learn through millions or even billions of trial and error mistakes takes a massive amount of training time. It is incredibly computationally expensive, requiring gigantic server farms. On top of all that, designing the right reward system is notoriously tricky. I mean, if you reward a digital robot simply for moving forward as fast as possible, it might not learn to walk. It might just learn to continuously fall forward because, well, technically that gets it closer to the finish line. Section 4, the climax, comparing the three types. Okay, now that we've walked through all three teaching methods, let's pull all these threads together. Look at the main goals here. Supervised learning predicts outcomes using specific, labeled answers. Unsupervised learning discovers hidden patterns using raw, unlabeled data. And reinforcement learning decides actions by seeking rewards in an interactive environment. They each serve entirely different purposes depending on the problem at hand, giving computer scientists a really versatile toolkit for almost any challenge. Now, while all three form the absolute foundation of modern AI, supervised learning currently takes the crown as the most widely used in real-world applications. Why is that? Well, because massive labeled datasets, like a company's historical sales data, perfectly categorized emails, or heavily tagged medical records, are readily available for most common business problems. It provides the reliable, predictable results that industries demand right now. Finally, Section 5, the future of AI, beyond basic learning. We've seen the distinct lanes these technologies operate in, but you know what? Those boundaries are rapidly beginning to blur. Tomorrow's AI systems aren't just relying on one single method. Researchers are actively combining these learning approaches to build far more intelligent, flexible systems. The ultimate goal is to create AI that can learn from significantly less labeled data, adapt incredibly quickly to environments it has literally never seen before, and make entirely autonomous decisions to solve multi-layered, evolving problems in real time. As these learning methods become even more powerful, combining the precision of supervised learning, the raw discovery of unsupervised learning, and the strategic decision-making of reinforcement learning, it leaves us with one final, fascinating thought to ponder. If these systems are already learning to navigate our world perfectly through their own digital experiences, what happens when AI learns to solve problems we haven't even discovered yet? Take a moment to think about that. Thank you so much for joining me on this explainer, and keep your curiosity sharp.